We're going to look here real fast at complex ions and formation constants once again. We looked at these back with the Lewis acids and Lewis bases, but they can be really helpful, especially when combined with a KSP expression. So we've already seen, for example, in lab and in lecture, some complex ions. It's usually a transition metal with different ions around it, different Lewis bases. The transition metal is the Lewis acid, and the things with lone pairs on them are great Lewis bases. Formation constant, again, is just taking the individual pieces to make the complex ion. So for the AgCN2 thing, you would have 1 silver and 2 cyanides as your reactants, and the complex ion would be the product. So notice this is kind of the opposite of KSP. KSP had the solid as a reactant, and the products were the ions. And here it's like the ions are the reactants and the complex ions are the products. But anyway, the KF for this one, 5.6 times 10 to the 18th, very large, very product favored. They form really easy. They freak chemists out sometimes when they don't understand what's all going on. This is the joy of the formation constant. Formation constants can be looked up in tables just like KSPs or KAs or anything like that. And again, notice that all of these numbers here are pretty big numbers. That means all of these complex ions are ready to form, ready to go. In these kind of KF expressions, remember the ions are the reactants and the complex ion is the product. They're almost always written as net ionic reactions, similar to what the KSPs were too, just FYI about that. So remember about complex ions, you're usually going to use a net ionic reaction. You don't include the spectator ions like we talked about in Chem 221. We talked about how you can use ammonia to help dissolve silver chloride, and this is just another example showing this process. Silver chloride is very insoluble, but if you want the silver chloride to be dissolved, i.e. to get off your glassware, adding ammonia will actually make the silver ion complex with it, and the complex ion then will pull the silver chloride away. Here's the KSP expression for silver chloride. Silver chloride solid going to silver ions and chloride ions. Let's combine that now with a KF expression. And remember, KF, the ions that go into it are the reactants, and the complex ion is the product. Well, if you combine these two reactions together, you can actually calculate the net K for this kind of reaction. Notice how silver ion will cancel on both sides. You can see what happens. In this case, the silver ion cancels. K net would be KSP times KF. KSP and KF are both numbers that are fairly easy to solve. And again, you will see your silver chloride dissolve.
When solutions of silver nitrate and sodium chloride are mixed, insoluble silver chloride precipitates from solution. When we add ammonia to the mixture, however, the precipitate redissolves. When ammonia is added to a mixture of solid and aqueous silver chloride, the ammonia serves as a Lewis base. The complex ion formed consists of 2 ammonia molecules bound to each silver ion. Formation of the complex lowers the concentration of silver in solution, which changes the solubility equilibrium.
This used to really freak chemists out, all right, because like you're making silver chloride and you're like, oh, no problem, but oh, you accidentally add the wrong thing, and sometimes these complex ions start kicking in. So the main point of bringing this up is just to remind you that KSP's solid reactant and the ions that make up the solid are the products, but KF's for formation constants for complex ions, the ions that go into it are the reactants, and the complex ion is the product. It's kind of the opposite. So just remember that in the back of your mind.